Hello friends, I've got a really snack-sized video for you today. We're gonna tackle quantum entanglement. This is just intuition video, okay? So it's not gonna be real quantum entanglement, but let me just this is an analogy of how to explain quantum entanglement to your 4-year-old child, for example, or something along those lines. So you know how usually you'll have a function psi wave function, and it'll be something like a tensor product between two like disjoint Hilbert spaces, whatever. You'll have something like that, right? Or mathematicians such as myself, I guess, would write this little guy to denote the tensor product. Cool. Okay. And so you know how for each psi, right? For each psi, you will assign a phi state. This is how tensors work. Like, just think of a tensor in general relativity, for example, or just a matrix, right? A matrix M. So for each index A in the matrix, you have all the other indices. Like your matrix is something like this. M11, M12, M13, so on, M1D, right? And so for each maybe this is the ith column, right? So for each ith row, you'll have d of them, right? So when you have a tensor product, your dimensions go up radically, right? So if you've got like, yeah, okay, you get it. It's easy stuff. Okay, and now, why do things get entangled? Well, let's say that your psi is comprised this is pausing for effect. So let's say that this is A and this is B. Let's not call this psi. We'll call this big A. Okay. So these are two lengths. Okay, I measure the length A and I measure the length B on the real line. No problemo, right? So if I give you a length, you know what it is. Like if I say A equals 10, you know what A is, right? No problem. Cool. Okay. Now let's say that we make an area, capital A. We make an area, capital A, of the vectors. Let's say vectors, right? It could be a cross product. Cross product. That's a great analogy. So you've got like length A, length B, and they make an area. They make an area A, right? Now let's say we fix that area. We say A is 1 because it's normalized, right? Like everything we like, everything is normalized. The area is 1. Well, if I had said the length is 1, that would be easy. We would know that if small a or small b is 1, then small a or small b is 1. No problem. But if big A, and by the way, big A is A times B, if big A is equal to 1, that doesn't tell me what A is or what B is. Small a, small b, right? I just know from this, perhaps, that B is 1 over A. That's all I know. So in this case, I want to say that small a and b are entangled. Why? If you choose a value for one, if you observe one, you know the value of the other. You don't need to check it. So you know that, I don't know why I'm pointing myself. So you know the area is 1, but you don't know either of the two values, and when you measure one, you get the value of the other. There's your entanglement. A and B, entangled. They could be in any state until you measure one of them. You measure the other one, bam. I can even give you an example. Let's do an experiment. Let's say A equals 2. Ooh, bam, I measured A, so then B is 1/2. B just collapsed. We got quantum decoherence on this square. Okay, that's it. That's the video. Now you can explain quantum mechanics to your child. Bye.